After 46 years of traveling through space, Voyager 1 finally sent back data from beyond our solar system that nobody saw coming. This isn't just another space mission update, it's a complete game changer for everything we thought we knew about the universe. The tiny spacecraft has crossed into interstellar space and discovered an environment so strange and structured that scientists are, honestly, rewriting their textbooks. Get ready to have your mind blown by what's really lurking in the darkness between stars, because the truth is absolutely incredible.
The Great Silence and Revival.
Space exploration hit a terrifying moment in late 2023 when humanity's most distant messenger went completely silent. Voyager 1, our faithful explorer that had been sending data for nearly 5 decades, suddenly started transmitting nothing but garbled, meaningless signals. Engineers at NASA faced an unprecedented challenge, performing brain surgery on a spacecraft using 1970s technology from 15 billion miles away. The culprit was a corrupted memory chip, likely destroyed by the same cosmic rays Voyager was studying. The fix required rerouting decades-old code into backup systems while dealing with a 22-hour communication delay. By April 2024, the impossible happened. Voyager came back to life, and what it began transmitting would change our understanding of space forever.
The Magnetic Revelation.
Something extraordinary happened when Voyager's magnetometer came back online. It revealed that space between stars operates by completely different rules. The spacecraft detected an interstellar magnetic field that's dramatically misaligned with our sun's magnetic influence, suggesting Voyager has encountered a galactic-scale boundary zone. These aren't minor variations. They're fundamental structural differences that point to magnetic turbulence zones where galactic fields twist and reconnect in ways scientists never predicted. The readings indicate Voyager might be navigating through invisible cosmic highways where magnetic forces create pathways and barriers throughout our galaxy. This discovery means the Milky Way has an underlying magnetic skeleton that influences everything from star formation to the flow of cosmic material, and we're only now getting our first direct measurements of this hidden architecture.
The Cosmic Storm.
The moment Voyager 1 crossed the heliopause in 2012, it encountered a radiation environment so intense it would be lethal to any human traveler. High-energy cosmic rays, accelerated to nearly light speed by distant supernovae and black holes, bombard the spacecraft at rates dramatically higher than anything measured inside our solar system. The jump wasn't gradual, it was like stepping through an invisible force field into a cosmic shooting gallery. These measurements reveal that our sun's protective bubble shields Earth far more effectively than anyone realized, creating a cosmic oasis in what's essentially a galaxy-wide radiation storm. The pattern of these particles isn't random either. Voyager has detected systematic variations suggesting natural radiation corridors that could represent the aftermath of ancient stellar explosions that shaped our galactic neighborhood millions of years ago.
The Whispering Void.
Forget everything you've heard about the silence of space. Voyager 1 has discovered that interstellar space is actually humming with constant activity. The spacecraft's plasma wave instrument detects persistent low-frequency oscillations that create a cosmic soundtrack most people will never hear. These aren't just random noise. They're organized pressure waves moving through space like invisible weather fronts. Multiple density spikes indicate Voyager is encountering shock fronts left behind by ancient supernovae that exploded thousands of years ago, with their energy still rippling through the cosmic medium. The most fascinating discovery is how layered this environment appears to be. Some regions are hotter, others denser, creating distinct climate zones in what we assumed was uniform emptiness. This cosmic weather system suggests interstellar space has its own complex meteorology.
Mapping the Invisible Galaxy.
Every data packet Voyager 1 transmits is helping scientists construct something unprecedented, a three-dimensional navigation map of interstellar space. The spacecraft has become humanity's anchor point for understanding the Milky Way's invisible infrastructure, measuring cosmic ray gradients, particle densities, and magnetic field orientations that reveal the hidden structure of our galactic neighborhood. This isn't theoretical modeling anymore, it's real-world cartography of the cosmos, like having a weather satellite for space between stars. The radiation mapping has profound implications for future human space exploration, as the intensity of interstellar radiation is far more dangerous than what astronauts encounter in Earth orbit. Understanding where natural shields and danger zones exist could determine whether humans can ever safely venture beyond our solar system, making Voyager's measurements crucial for planning humanity's next giant leap into deep space.
The cloudlet highway.
Since entering interstellar space, Voyager 1 has passed through at least 2 distinct interstellar cloudlets, regions where plasma, dust and gas density suddenly changes by factors of 2 to 3 times. These discoveries reveal that the space between stars resembles an ocean with currents, eddies, and weather patterns, rather than the uniform void astronomers once imagined. The probe's instruments show evidence of structured plasma ripples with clear boundaries and characteristics, suggesting large-scale organization in what scientists thought was chaos. NASA researchers now believe our sun is moving through the local interstellar cloud, with Voyager helping define its outer edges inside the much larger local bubble, an enormous cavity created by ancient supernovae explosions. These density shifts could affect Earth's exposure to cosmic radiation over millennia, as our solar system drifts through different interstellar environments, potentially influencing everything from cloud formation to biological mutation rates.
The galactic boundary zone.
So the transition from our solar system to interstellar space turned out to be, well, far messier and more complex than anyone predicted. Voyager 1 revealed that crossing the heliopause isn't like passing through a clean boundary. It's more like navigating a chaotic swirl of plasma, radiation, and magnetic forces that shift and change as our sun moves through the galaxy at 450,000 miles per hour. The boundaries Voyager crosses aren't fixed structures but dynamic zones that evolve constantly. Magnetic fields don't align as expected, radiation environments change dramatically over short distances, and plasma waves suggest ongoing activity that scientists are only beginning to understand. This complex interstellar weather creates an environment where the edge of our solar system becomes less of an edge and more of a turbulent frontier zone, where solar and galactic influences battle for dominance in an invisible cosmic wrestling match.
The ancient supernova trail.
The systematic patterns Voyager 1 detects in cosmic ray intensity and plasma density aren't just random fluctuations, they're actually geological records of our galaxy's violent past, written into the very fabric of space itself. The spacecraft appears to be following trails left behind by supernova explosions that happened millions of years ago, with their shockwaves still carving out pathways through the interstellar medium. These cosmic highways, you could say, channel high-energy particles along preferred routes, and that's what creates the radiation gradients and magnetic field orientations Voyager measures. Some astrophysicists even believe these ancient stellar explosion patterns might influence where new stars form in our part of the galaxy, with magnetic field orientations potentially guiding cosmic material into denser regions that could trigger future star birth. So, the data suggests Voyager isn't just sampling local conditions, it's really giving us a glimpse into the aftermath of cataclysmic events that shape the structure of our entire galactic neighborhood over, well, cosmic timescales.
The Eternal Ambassador.
While Voyager 1's scientific mission might end within a few years as its power source slowly fades, the spacecraft's journey through eternity is actually just beginning. This small probe will keep silently coasting through the cosmos long after human civilization has either evolved beyond recognition or, disappeared entirely. In about 40,000 years, Voyager will make its closest approach to Gliese 445, a red dwarf star, passing within about 1.6 light-years. It's kind of like a celestial handshake across the vastness of space. The golden record attached to Voyager carries sounds, music, greetings in 55 languages, and 116 images from Earth, all engineered to survive over 1 billion years in the harsh environment of space. This makes Voyager not just a scientific instrument, but possibly the most enduring monument humanity will ever create, carrying the essence of our species into the cosmic deep, long after Earth's continents have shifted beyond recognition.
The real discovery.
The most profound revelation from Voyager 1's journey isn't about discovering aliens or wormholes. It's really about understanding that interstellar space is a dynamic, structured environment all its own, with weather patterns, magnetic topography, and radiation zones. The spacecraft revealed that our solar system exists within a kind of protected oasis, with the sun's heliosphere shielding us from an environment that's way more intense and radiation-filled than anyone realized. The transition to interstellar space isn't simple, it's messy and complex, with magnetic fields that don't line up the way we expected, and plasma waves that show constant activity. The interstellar medium has layers, fronts, and boundaries that shape the invisible architecture of our galaxy. Most importantly, Voyager showed us that we live in a cosmic shelter. Our solar system isn't just our home, it's really our sanctuary in a galactic storm raging beyond our protective bubble, making Earth even more precious than we ever imagined. So there you have it. Voyager 1 didn't just reach the other side, it discovered that the other side is nothing like we expected. Which part surprised you the most about interstellar space? Let me know in the comments below. If you enjoyed learning about humanity's greatest space exploration achievement, make sure to like this video, share it with someone who loves real science as much as you do, and don't forget to subscribe to Sci and Y for more mind-blowing discoveries about our incredible universe. Until next time, keep questioning and keep exploring. The Juno spacecraft has been revolutionizing our understanding of Jupiter since its arrival in 2016. Its deep scans beneath the clouds have revealed mysteries that challenge everything we thought we knew about the gas giant. Beneath Jupiter's swirling atmosphere lies not just storms, but an enigmatic heart pulsing with powerful forces unlike anything seen before. From terrifying cyclones spinning backwards to a fuzzy core that defies physics, Juno's discoveries are rewriting textbooks. Today we're diving into the most shocking revelations about the largest planet in our solar system. The mysterious central storm discovery. Juno's ultraviolet and microwave instruments uncovered something absolutely terrifying at Jupiter's core, a massive cyclonic storm that shouldn't exist according to our understanding of planetary physics. Unlike the surface storms we can observe from Earth, this central storm spins in the opposite direction to Jupiter's rotation and measures approximately 10,000 kilometers wide, making it larger than Earth itself. In 2017, scientists led by Dr. Scott Bolton from the Southwest Research Institute first reported this bizarre storm that completely defied existing models of Jovian weather patterns and atmospheric dynamics. The storm's presence suggests Jupiter's interior is far more violent and chaotic than anyone previously believed, with turbulent motions that create powerful electromagnetic effects and possibly influence the planet's extraordinary auroras. This discovery opened terrifying new questions about how gas giants maintain their internal heat sources and complex weather systems, forcing scientists to completely rethink everything they thought they knew about planetary atmospheres. The central storm's backwards rotation indicates incredibly complex internal dynamics that researchers are still desperately trying to understand, representing one of the most significant and disturbing findings from Juno's exploration of Jupiter's mysterious depths. The beginning of the mission. Launched on August 5, 2011, the Juno spacecraft embarked on a nearly 5-year journey through the hostile depths of space to reach Jupiter, finally arriving on July 4, 2016. The spacecraft's primary mission was to understand Jupiter's formation, atmospheric composition, massive magnetosphere, and complex gravity field through unprecedented close-range observations. Equipped with sophisticated instruments including the microwave radiometer and Jovian infrared auroral mapper, Juno follows a highly elliptical orbit around Jupiter every 53 days, diving dangerously close through the planet's radiation-filled cloud tops. Mission Commander Scott Bolton and NASA engineering teams spent years developing meticulous protection systems to shield Juno from Jupiter's deadly radiation belts, designing a specialized titanium radiation vault to protect the spacecraft's sensitive electronics from being fried by the intense electromagnetic environment. This groundbreaking mission continues to push the absolute limits of planetary science and space exploration technology, offering humanity's best and closest look yet at the gas giant's mysterious core and incredibly complex magnetic environment. The spacecraft's highly elliptical orbit allows it to approach within just 4,200 kilometers of Jupiter's cloud tops during each perijove pass, collecting detailed measurements and data that were previously completely impossible to obtain. Jupiter is the world of chaos. Jupiter represents the ultimate manifestation of atmospheric chaos in our solar system, with weather patterns so violent and unpredictable, they make Earth's most severe storms look like gentle breezes. The planet's massive atmosphere consists primarily of hydrogen and helium gases, generating vertical wind speeds that regularly exceed 540 kilometers per hour, fast enough to tear apart any spacecraft attempting to enter its atmosphere. Jupiter's cloud layers reveal constantly shifting bands of storms, massive vortexes, and lightning strikes that are thousands of times more powerful than anything experienced on Earth. These storm systems create extraordinary geometric patterns and vivid colors visible even through telescopes millions of kilometers away, painting Jupiter's surface in bands of orange, brown, and white. Juno's advanced observations confirmed the presence of massive lightning storms detected by its Jovian Energetic Particle Detector instrument, which identifies highly energetic particles directly linked to these violent and unpredictable weather systems. This incredible atmospheric complexity makes Jupiter not merely a gas giant, but a living laboratory for studying extreme atmospheric dynamics and fundamental physics of fluid turbulence, operating at scales completely impossible to replicate on Earth. The planet's differential rotation means different latitudes rotate at dramatically different speeds, creating powerful shear forces that generate Jupiter's distinctive banded appearance. Io, the volcanic moon. Among Jupiter's 79 confirmed moons, Io stands out as the most volcanically active and geologically violent body anywhere in our solar system, making it a hellish world of constant eruptions and molten chaos. Its scarred surface is covered with hundreds of active volcanoes that continuously spew sulfur compounds and molten lava fountains reaching incredible heights of up to 500 kilometers above the surface. This relentless volcanic fury results from intense tidal heating caused by Jupiter's massive gravitational pull, combined with complex orbital resonances with neighboring moons Europa and Ganymede, creating internal friction that keeps Io's interior molten. Juno's detailed flybys and precise measurements combined with archival data from previous missions like Galileo help scientists understand Io's extreme geological processes and its crucial role in feeding charged particles into Jupiter's deadly magnetosphere. Io's plasma torus, a massive ring of highly ionized gases orbiting around Jupiter, directly influences the planet's radiation environment and provides essential insights into the complex interactions between Jupiter and its satellite system. The moon's sulfur-rich volcanic activity creates a unique and hostile environment, where surface temperatures vary dramatically from extremely cold regions in permanent shadow to areas heated to over 1,800 degrees Celsius by continuous volcanic activity, making Io one of the most geologically dynamic and dangerous worlds. Research on Jupiter's magnetic field. Juno's sophisticated magnetometer instruments have been absolutely crucial in mapping Jupiter's unprecedented magnetic field, which represents the strongest planetary magnetic field in our entire solar system, measuring approximately 14 times more powerful than Earth's protective magnetic shield. This immense magnetic field extends millions of kilometers into space, creating Jupiter's vast magnetosphere that completely dwarfs even the Sun's magnetic influence in the immediate vicinity of the giant planet. Leading scientists, including Dr. Heidi Becker from NASA's Jet Propulsion Laboratory, discovered completely unexpected asymmetries and highly localized regions of intense magnetism during Juno's dangerously close orbital passes through Jupiter's radiation belts. These groundbreaking findings strongly suggest incredibly complex dynamo action occurring deep beneath Jupiter's cloud layers, generated by powerful currents of flowing metallic hydrogen existing under extreme pressure in the planet's mysterious interior regions. Understanding this magnetic environment represents far more than just studying Jupiter. It provides essential insights into planetary magnetic field generation and the protective roles these fields play around worlds throughout the universe. The magnetic field's highly irregular and unpredictable structure clearly indicates that Jupiter's internal dynamics operate through mechanisms far more complex and violent than scientists previously imagined, with profound implications for understanding how massive planets generate and maintain their protective magnetic environments. Juno mission peaks under Jupiter's surface. Juno's precision gravity science investigation revealed one of the most shocking discoveries in planetary science. Jupiter's core is not the compact, solid metallic ball that scientists expected, but instead appears to be a fuzzy, diluted structure extending up to 50% of the planet's total radius. This absolutely astonishing discovery completely challenged and overturned previous models of gas giant planet formation that had been accepted by the scientific community for decades. Detailed gravitational data from the spacecraft indicates that heavy metallic elements are far more spread out throughout Jupiter's interior than anyone predicted, mixing extensively with lighter hydrogen and helium gases in a diffuse, semi-solid core structure. The international research team, led by Dr. Luciano Ies from Sapienza University of Rome, used incredibly precise spacecraft tracking techniques to measure subtle variations in Jupiter's complex gravity field, revealing these hidden internal structures that were completely invisible from external observations. These revolutionary results strongly suggest that Jupiter experienced an extremely violent and chaotic formation history involving massive planetary collisions or prolonged turbulent accretion periods during the early solar system's development. Unveiling this incredible complexity hidden beneath Jupiter's deceptively calm-looking cloud layers provides invaluable scientific clues about gas giant origins, evolution, and the fundamental processes that shape planetary formation throughout the universe, suggesting that giant planets form through far more chaotic and violent processes than previously understood. Jupiter's formation and composition. Jupiter formed approximately 4.5 billion years ago during the earliest phases of our solar system's chaotic development, primarily accumulating vast quantities of hydrogen and helium gases captured directly from the swirling protoplanetary disk surrounding the young sun. Its absolutely massive size, containing over 320 times Earth's total mass, provided sufficient gravitational power to retain these extremely light gases that smaller rocky planets like Earth and Mars could never hope to capture or hold. Juno's advanced spectral observation instruments confirm the presence of trace amounts of water vapor, ammonia, and methane compounds, distributed at varying depths throughout Jupiter's complex atmospheric layers, creating a chemical fingerprint of the planet's formation history. The presence and distribution of these molecular compounds helps scientists reconstruct the primordial materials that Jupiter accumulated during its formation, and provides crucial data about the radial mixing and chemical evolution of compounds over billions of years. Leading research by planetary atmospheric scientist Dr. Lee Fletcher from the University of Leicester enhances sophisticated computer models of Jupiter's atmospheric composition, revealing complex chemical gradients that indicate dynamic upwelling processes and vertical mixing of gases from deep interior regions. Understanding Jupiter's formation process and chemical evolution significantly improves scientific theories about planetary system development and helps predict the potential characteristics and formation mechanisms of gas giant exoplanets orbiting distant stars throughout our galaxy. Jupiter as Earth's protector. Jupiter functions as a massive celestial guardian for Earth and the inner solar system, using its immense gravitational influence to deflect or capture dangerous incoming comets and asteroids that could potentially cause catastrophic impacts on our planet. The planet's enormous magnetosphere and powerful gravitational field significantly reduce the impact rate of potentially hazardous objects in the inner solar system, possibly providing crucial protection that has allowed complex life to evolve and thrive on Earth over billions of years. However, Jupiter's protective role represents a complex double-edged sword. While its gravity shields us from many threats, it can also gravitationally perturb objects and send them on altered trajectories that intersect with Earth's orbital path around the Sun. Comprehensive studies by leading astronomers including Dr. Alan Stern from the Southwest Research Institute emphasize this complicated dual role, examining how Jupiter simultaneously facilitates both planetary protection and potentially dangerous dynamical chaos within our solar system's architecture. Understanding this delicate gravitational balance proves essential for accurately assessing the long-term evolution of Earth's environment and evaluating the likelihood of maintaining stable, life-supporting conditions necessary for biological evolution on planets and other star systems. Jupiter's gravitational influence has fundamentally shaped the orbital architecture of our entire solar system over billions of years, creating complex resonance patterns that affect asteroid and comet trajectories, ultimately influencing the delivery of water and organic materials to inner planets during their formation. The Great Red Spot Mystery. The Great Red Spot represents one of the most iconic and mysterious features in our solar system, a colossal storm system larger than Earth that has been continuously raging for several centuries, yet recently has been mysteriously shrinking at an alarming rate. First definitively observed and documented by astronomers in the 17th century, this massive anticyclonic storm currently spans approximately 16,000 kilometers across and rotates counterclockwise at terrifying speeds exceeding 432 kilometers per hour, creating winds powerful enough to destroy any human-made structure. Juno's sophisticated scientific instruments detected incredibly complex multi-layered cloud structures and intense lightning activity deep within the storm system, providing revolutionary new insights into the energy sources and physical mechanisms that have maintained this enormous weather phenomenon for hundreds of years. Leading researchers, including Dr. Heidi Becker from NASA's Jet Propulsion Laboratory, actively study the complex atmospheric dynamics driving the Great Red Spots concerning shrinkage and investigate potential changes in Jupiter's atmospheric composition, or internal energy flow patterns. The storm exemplifies the most powerful and persistent meteorological phenomena known to science, challenging our fundamental understanding of fluid mechanics and atmospheric physics operating on truly planetary scales. Recent detailed observations suggest the Great Red Spot may be gradually losing both its distinctive reddish coloration and its well-defined structural boundaries, raising serious scientific questions about whether this iconic feature will eventually disappear entirely, fundamentally altering Jupiter's appearance forever. Jupiter's rings and lesser moons. Jupiter possesses a surprisingly complex but faint ring system that was first discovered in 1979 by the Voyager 1 spacecraft during its historic flyby, revealing a delicate structure composed primarily of microscopic, dust-sized particles continuously supplied by meteoroid impacts on the planet's small inner moons. These rings, while dramatically less spectacular than Saturn's magnificent and well-known ring system, remain incredibly thin and faint, but play a surprisingly important role in Jupiter's complex magnetospheric environment and particle dynamics. Juno's detailed observations, combined with data from earlier exploratory missions, have identified 4 distinct main ring components and dozens of small, irregularly shaped moons existing within Jupiter's intense radiation-filled magnetosphere. Among these lesser-known moons, Amalthea and Thebes serve as primary dust contributors to the ring system through continuous bombardment by high-velocity micrometeorites that blast material from their surfaces into space. Understanding these smaller celestial bodies and their dynamic ring interactions offers valuable scientific clues about Jupiter's long-term evolution and the fundamental physical processes that shape planetary ring systems throughout our solar system and beyond. The ring particles undergo continuous replenishment cycles through ongoing impacts on the small moons, creating a dynamic equilibrium system where material is constantly being added through collisions while simultaneously being lost through various gravitational and electromagnetic processes, providing crucial insights into the complex gravitational interactions governing ring systems around giant planets. That's the incredible story of Juno's journey deep beneath Jupiter's clouds, uncovering mysteries that force us to completely rethink our understanding of the giant planet. What surprised you the most about these terrifying discoveries? Let us know in the comments below. If you enjoyed diving into Jupiter's darkest secrets like this video, share it with fellow space enthusiasts, and don't forget to subscribe to Sci and Y for more amazing space exploration stories. Until next time, keep looking up. Voyager 1 is a breathtaking testament to human ingenuity and curiosity. Launched in 1977, this remarkably small spacecraft has traversed the vast reaches of the solar system and beyond, venturing where no human-made object has gone before, into interstellar space. As it now drifts deeper into the unknown, Voyager 1 continues to send back invaluable data about the cosmic environment beyond our sun's influence. Recent observations hint at phenomena that both challenge and confirm fundamental aspects of astrophysics, revealing mysteries that hold profound implications for our understanding of the universe. The birth of a star sailor. In the early 1970s, the Voyager program was conceived as a bold mission to explore the outer planets with unprecedented detail. The Voyager 1 spacecraft, roughly the size of a small car, was designed for durability and autonomy, equipped with a golden record, an interstellar message recording the diverse sounds and images of Earth. Directed by Dr. Ed Stone at NASA's Jet Propulsion Laboratory, the mission successfully navigated the grand tour of Jupiter, Saturn, Uranus, and Neptune, leveraging gravity assist to extend its reach. Despite limitations in technology at the time, Voyager 1 continues to operate nearly 45 years after launch, a marvel of engineering resilience still beaming secrets from the edge of the solar system. The spacecraft's design prioritized robust systems capable of operating autonomously over decades, with minimal intervention due to the communication delay of over 18 hours at the edge of the solar system. The mission also carried groundbreaking scientific instruments designed to analyze planetary atmospheres, magnetic fields, and charged particles. Voyager 1's findings redefined our understanding of planetary formation and magnetic dynamo processes, revealing complex interactions within gas giants that challenged established physics. Most remarkably, the probe's longevity has surpassed initial expectations, continuing to provide valuable data well into the 21st century. The Grand Tour. Voyager 1's Grand Tour was a triumph of celestial navigation and scientific ambition. Utilizing precisely timed flybys, Voyager 1 collected invaluable data about the gas giants, revealing dynamic atmospheres, complex ring systems, and magnetic phenomena previously undreamt. Under the stewardship of Flight Director Suzanne Dodd and project scientists at JPL, the spacecraft gained speed from gravitational slingshots at Jupiter and Saturn, ultimately escaping the solar system's grasp. Visuals of Jupiter's storms and Saturn's rings reshaped planetary science, inspiring a generation and setting the stage for interstellar exploration. Each encounter enriched our knowledge, paving the way for humanity's journey into the galactic abyss. The success of the Grand Tour opened doors for extended missions including Voyager 2 and Pioneer 10 and 11, setting a new standard for deep space exploration. Data transmitted reshaped our comprehension of planetary weather, magnetic environments, and ring systems, influencing models used in current astronomical research. Voyager 1's trajectory post-Saturn escape set the stage for humanity's first venture into interstellar space, marking a milestone achieved by no craft before. The meticulous planning and execution underpinning the mission exemplify the extraordinary human drive to explore beyond current horizons. The Golden Record. Embedded within Voyager 1 is the famous Golden Record, a time capsule crafted to communicate humanity's story to any extraterrestrial intelligence that might encounter it. Curated by a distinguished committee led by astronomer Carl Sagan, this 12-inch gold-plated copper disc includes greetings in 55 languages, music from diverse cultures around the world, and 116 encoded images depicting life on Earth. The record serves as a symbol of hope, friendship, and cosmic connection, acoustically traversing the vast gulf between stars as Voyager sails silently through the void. Its cover includes a pulsar map and scientific diagrams designed to communicate Earth's location in the galaxy to any intelligent beings who might find it. The selection process involved extensive deliberation about what aspects of human culture and knowledge would be most representative and comprehensible to alien minds. Beyond its scientific mission, the Golden Record transforms Voyager 1 into a cultural ambassador, carrying the essence of human civilization into the cosmos. This remarkable artifact represents humanity's first serious attempt at interstellar communication, embodying our deepest hopes for contact with other intelligent life forms in the universe. The record's contents reflect both our diversity and our common humanity, serving as a testament to Earth's rich cultural heritage. Years in the void. After completing its primary mission to the gas giants, Voyager 1 embarked on its extended journey through the outer solar system and beyond. For over 4 decades, this resilient spacecraft has continued to function in the harsh environment of deep space, enduring extreme cold, radiation bombardment, and the complete isolation of the cosmic void. Its instruments persistently measure solar wind particles, magnetic field strength, and cosmic ray intensity, delivering unprecedented insights into the heliosphere's structure and boundary. Despite operating far beyond its original design parameters, Voyager's radioisotope thermoelectric generators continue to provide sufficient power to maintain communication with Earth. The spacecraft's remarkable longevity has allowed scientists to study long-term variations in the solar system's outer regions and observe the gradual transition from solar-dominated to galactic-dominated space. Each data transmission, traveling over 14.5 billion miles to reach Earth, represents a triumph of human engineering and perseverance. Mission controllers have had to make increasingly difficult decisions about which instruments to keep active as power levels slowly decline. The probe's survival in this hostile environment has provided invaluable lessons for designing future deep space missions intended to explore even more distant destinations. Crossing the boundary. On August 25, 2012, Voyager 1 achieved a historic milestone by crossing the heliopause and entering interstellar space, becoming the first human-made object to leave the solar system. This momentous transition was marked by dramatic changes in the particle environment, a sharp increase in cosmic ray intensity, and a corresponding decrease in solar wind particles. Mission scientists led by Dr. Stamatios Krimigis carefully analyzed the data to confirm this unprecedented boundary crossing, which had been anticipated for years. The heliopause represents the edge of the heliosphere, the vast bubble of charged particles and magnetic fields created by our sun's solar wind. Beyond this boundary lies the interstellar medium, a realm filled with materials from other stars and the remnants of ancient stellar explosions. Voyager's instruments detected the sudden change in magnetic field orientation and particle composition that definitively proved it had entered this new domain. The crossing provided the first direct measurements of interstellar space, confirming theoretical predictions while also revealing unexpected complexities in the boundary region. This achievement marked the beginning of a new era in space exploration, as humanity finally had a probe operating in the galactic environment. The data collected during and after the crossing continues to reshape our understanding of how our solar system interacts with the surrounding galaxy. Signals from nowhere. In recent years, Voyager 1 has transmitted increasingly puzzling data that challenges our understanding of interstellar space. The spacecraft has detected mysterious plasma wave oscillations and unexpected magnetic field fluctuations that appear to have no obvious source or explanation. Dr. Larry Esposito and his research team have identified these anomalous signals as potential evidence of previously unknown interstellar phenomena or structural irregularities in the galactic medium. The signals from nowhere suggest that the space between stars is far more dynamic and complex than previously imagined, with rich physical processes occurring in regions once thought to be relatively empty. These mysterious transmissions have sparked intense scientific debate, with some researchers proposing they indicate interactions with dense interstellar clouds or magnetic field reconnection events. Others suggest the signals might represent encounters with the shock waves of distant stellar explosions that have propagated across the galaxy for millions of years. The data patterns don't match any known astrophysical models, forcing scientists to reconsider fundamental assumptions about the nature of interstellar space. Voyager's continuing journey deeper into this mysterious realm promises to reveal even more surprising discoveries about the hidden dynamics of our galactic neighborhood. The temperature mystery. One of the most perplexing anomalies discovered by Voyager 1 involves unexplained temperature fluctuations that defy conventional understanding of deep space thermal dynamics. Despite moving steadily away from the sun and into the cold depths of interstellar space, the spacecraft's sensors have recorded puzzling warming events that contradict expected cooling trends. Dr. John Napick leads the engineering team investigating these thermal anomalies, which could result from several possible mechanisms, including interactions with interstellar dust particles or energetic cosmic ray bombardment. The temperature variations might also indicate encounters with warmer regions of the interstellar medium or internal spacecraft issues affecting sensor calibration. These thermal mysteries have significant implications for mission longevity, as temperature extremes can impact the performance and lifespan of critical onboard systems. Understanding these fluctuations is crucial for predicting how long Voyager's instruments will continue functioning and for designing thermal protection systems for future interstellar missions. The spacecraft's ability to endure such extreme and variable thermal conditions far exceeds original engineering predictions, providing valuable insights into spacecraft survivability in the harsh interstellar environment. Resolving the temperature mystery remains one of the mission's most important ongoing challenges, as it affects both scientific interpretation and operational planning. Changing course. Maintaining Voyager 1's precise trajectory and communication alignment has required increasingly sophisticated navigation techniques as the spacecraft ventures deeper into interstellar space. Under the expert supervision of Flight Director Suzanne Dodd, mission controllers have executed subtle but critical thruster maneuvers to counteract natural orbital drift and maintain optimal antenna pointing toward Earth. These delicate course corrections ensure that Voyager's weak radio signals, transmitted with just 20 watts of power, continue to reach NASA's Deep Space Network receivers despite the enormous distance. The navigation team faces unprecedented challenges in predicting and correcting the spacecraft's path, as traditional gravitational models become less applicable in the interstellar environment. Recent trajectory adjustments have revealed unexpected external forces acting on the spacecraft, possibly related to pressure from interstellar gases or magnetic field interactions. The precision required for these maneuvers is extraordinary, considering that Voyager is now traveling at over 38,000 miles per hour, relative to the Sun, and any navigation error compounds over vast distances. These course changes also provide valuable scientific data about the forces and conditions Voyager encounters in its interstellar journey. The ongoing navigation challenges demonstrate the remarkable dedication and expertise of the mission operations team in maintaining contact with humanity's most distant emissary. Ghost in the machine. Voyager 1's aging systems have begun exhibiting strange anomalies that mission engineers have dubbed the ghost in the machine. Unexplained glitches and data irregularities that seem to have no identifiable cause. The most prominent of these anomalies involves the spacecraft's attitude articulation and control system, which began sending garbled telemetry data that didn't match the probe's actual orientation and movement. Dr. Emma Woodfield leads the team investigating these mysterious system behaviors, which could result from cosmic ray damage, software degradation, or unexpected interactions between aging components. The anomalies became so severe that mission controllers temporarily lost the ability to determine Voyager's exact orientation in space, creating significant challenges for maintaining communication with Earth. After months of detective work, engineers managed to switch to a backup system and restore normal operations, but the incident highlighted the precarious nature of operating 46-year-old technology in the harsh interstellar environment. These ghost phenomena provide valuable insights into how spacecraft systems degrade over extreme timescales and help engineers design more robust systems for future long-duration missions. The successful resolution of these problems demonstrates the ingenuity and persistence of NASA's engineering teams in troubleshooting unprecedented technical challenges across interstellar distances. Patterns within patterns. Recent analysis of Voyager 1's scientific data has revealed intricate and unexpected patterns within the interstellar medium that suggest a far more complex and structured galactic environment than previously imagined. Dr. Harold Kruger directs ongoing research that has identified filamentary structures, spiral magnetic field configurations, and turbulent plasma waves swirling around the spacecraft's location. These patterns within patterns indicate sophisticated magnetic and energetic phenomena operating on multiple scales throughout interstellar space, from local turbulence to vast galactic structures. The observations suggest that the space between stars is not empty void but rather a dynamic, ever-changing medium filled with invisible currents and forces that shape the galactic environment. Voyager's measurements have detected evidence of shock waves from ancient stellar explosions, magnetic field boundaries between different regions of space, and complex interactions between interstellar gas and cosmic ray particles. These discoveries are revolutionizing our understanding of galactic physics and the processes that govern matter and energy flow throughout the Milky Way. The patterns Voyager observes may represent the fundamental architecture of our galaxy, revealing how stars, gas, and magnetic fields interact to create the large-scale structure we see in the cosmos. Each new data transmission adds another piece to this cosmic puzzle, gradually unveiling the hidden dynamics that govern our galactic home. Voyager 1's extraordinary journey continues to astonish scientists and space enthusiasts worldwide as it ventures deeper into the unknown reaches of interstellar space. The mysterious phenomena and unexpected discoveries it encounters challenge our fundamental understanding of the cosmos while revealing the incredible complexity of the galactic environment. What aspect of Voyager's journey fascinates you most? Share your thoughts in the comments below and subscribe to Sci and Y for more incredible stories of cosmic exploration and discovery. Until next time, keep looking up and wondering about the vast universe around us.
Welcome to Sci and Y, where we decode the mysteries of our universe through rigorous scientific analysis. Today, we're investigating the enigmatic interstellar visitors that have astronomers worldwide questioning everything we thought we knew. From the puzzling Oumuamua to the massive newcomer 3I Atlas, these cosmic wanderers challenge our understanding of what's possible in the vast expanse of space. Join us as we explore the data, examine the theories, and ask the fundamental question, are we alone? Oumuamua Discovery and Anomalies. In October 2017, the Pan-STARRS survey in Hawaii detected something unprecedented, Oumuamua, the first confirmed visitor from another star system. This elongated object, measuring approximately 800 meters in length with an extreme 10:1 aspect ratio, defied all known classifications of celestial bodies. What truly baffled scientists was its unexplained acceleration away from the Sun without any detectable cometary outgassing or tail formation. Traditional physics couldn't account for this behavior, leading to intense scientific debate. Harvard astrophysicist Avi Loeb proposed the controversial hypothesis that Oumuamua might be an artificial light sail constructed by extraterrestrial intelligence. Other researchers suggested more conventional explanations, including exotic compositions like hydrogen or nitrogen icebergs. However, each natural explanation faced significant challenges when confronted with observational data. The object's discovery fundamentally altered our approach to studying interstellar space, revealing that the void between stars isn't as empty as previously believed. Despite extensive analysis using multiple space and ground-based telescopes, Oumuamua's true nature remains one of astronomy's greatest mysteries. UFO and UAP encounters and theories. The scientific community has increasingly focused on unidentified aerial phenomena following credible reports from U.S. Navy personnel. The most documented case was in 2004, an encounter with the infamous Tic Tac object off California's coast. This white, featureless craft demonstrated flight characteristics that violate known aerodynamic principles, including instantaneous acceleration and seemingly impossible maneuvers. Multiple radar systems tracked the object simultaneously while trained pilots provided visual confirmation. Some researchers have proposed advanced theories to explain these phenomena, including plasma-based holographic projections or exotic propulsion technologies. The physics of such systems would require manipulation of electromagnetic fields on scales currently beyond human capability. Government acknowledgement of retrieved crashed objects has added credibility to these reports, with intelligence sources confirming multiple recoveries. The correlation between increased UAP sightings and humanity's growing space-based observation capabilities raises intriguing questions about potential monitoring activities. Advanced civilizations might employ sophisticated surveillance technologies to assess emerging technological species without direct contact. Bob Lazar analysis. Bob Lazar's claims about reverse-engineered extraterrestrial technology at Area 51 have influenced UFO research for decades, despite ongoing scientific skepticism. His detailed descriptions of anti-gravity propulsion systems powered by element 115 seemed purely fictional in the 1980s, yet this super-heavy element was successfully synthesized in laboratories in 2003. Lazar described witnessing craft that manipulated gravitational fields through bombardment of element 115 with protons, creating localized distortions in spacetime. While his educational credentials remain unverifiable and security clearance claims are disputed, some aspects of his technical descriptions align with emerging theoretical physics concepts. The Alcubierre warp drive equations, published after Lazar's claims, describe similar spacetime manipulation techniques for faster-than-light travel. Modern physics recognizes that gravity is indeed a manifestation of curved spacetime, making field manipulation theoretically possible with sufficient energy control. However, the energy requirements for such technologies would exceed current human capabilities by orders of magnitude. Lazar's influence on UFO culture persists because his descriptions aren't entirely inconsistent with advanced theoretical physics. Light sail hypothesis. Professor Avi Loeb's revolutionary light sail hypothesis represents a paradigm shift in how we interpret anomalous astronomical observations. His mathematical analysis demonstrates that radiation pressure from stellar light could account for Oumuamua's mysterious acceleration if the object possessed specific physical characteristics. For photon pressure to explain the observed forces, the object would need to be extremely thin, less than a millimeter, while maintaining structural integrity across interstellar distances. This requires materials with strength-to-weight ratios far exceeding natural substances, suggesting advanced engineering. Loeb's calculations show that such a sail could maintain stable flight patterns across vast cosmic distances, making interstellar travel feasible for sufficiently advanced civilizations. The hypothesis gained attention because it elegantly resolves the contradiction between Oumuamua's acceleration and lack of visible outgassing. Critics argue that natural explanations involving exotic ices remain more probable, but Loeb maintains that scientific objectivity demands consideration of all possibilities. His work has reinvigorated the search for extraterrestrial intelligence by demonstrating how conventional astronomical surveys might detect technological signatures from advanced civilizations. 3I Atlas, the new discovery. The discovery of 3I Atlas in early 2025 by the Asteroid Terrestrial Impact Last Alert System has sent shockwaves through the astronomical community. Initial observations suggest this interstellar visitor measures between 10 to 20 kilometers in diameter, making it potentially 200 times larger than Oumuamua, a size disparity that challenges statistical models of interstellar object populations. The object's velocity exceeds 60 kilometers per second, confirming its extrasolar origin through hyperbolic trajectory analysis. What makes 3I Atlas particularly intriguing is its unusual brightness and spectroscopic signatures suggesting metallic surface composition inconsistent with typical asteroids or comets. NASA's James Webb Space Telescope has detected infrared emissions indicating possible thermal management systems and structured materials. Unlike natural objects that should tumble chaotically through space, 3I Atlas appears to maintain stable orientation and controlled energy output. The statistical probability of discovering such a massive interstellar object as only our third detection approaches astronomical improbability. Advanced spectroscopic analysis reveals isotopic ratios unlike any solar system materials, supporting theories of formation in drastically different stellar environments. Atlas Telescope System. The Atlas network represents a revolution in automated astronomical surveys, utilizing 4 strategically positioned telescopes across Hawaii, Chile, and South Africa to monitor the entire visible sky. Each telescope, despite its modest 0.5-meter aperture, employs cutting-edge CCD arrays and sophisticated software algorithms capable of detecting objects moving against the stellar background. The system's strength lies in its temporal resolution. Scanning the complete sky every 24 hours enables detection of extremely fast-moving objects that traditional surveys would miss. Atlas technology, developed through collaboration between the University of Hawaii and NASA's Planetary Defense Coordination Office, processes millions of astronomical images using machine learning algorithms trained to identify anomalous motion patterns. The detection of 3I Atlas demonstrates the system's capability to catch interstellar visitors early in their solar system transit, providing crucial observation time before they disappear into deep space. Real-time data processing flags suspicious objects within hours of detection, triggering follow-up observations from major observatories worldwide. This automated approach has transformed asteroid detection from periodic manual surveys to continuous automated monitoring. Scientific theories and debates. The scientific community remains fractured over explanations for 3I Atlas's anomalous properties, with competing hypotheses attempting to reconcile observational data with known physics. The hydrogen iceberg theory proposes the object consists of solid hydrogen formed in the frigid depths of interstellar space, though this model struggles to explain structural stability over millions of years. Alternative nitrogen sublimation models suggest composition similar to Pluto's surface, potentially explaining observed outgassing without visible tail formation. Dr. Alan Fitzsimmons leads the natural origin camp, emphasizing the need for comprehensive spectroscopic data before considering exotic explanations. Conversely, advocates for expanded theoretical frameworks that might accommodate artificial construction scenarios. The fundamental problem remains the inconsistency between observed acceleration patterns and minimal detectable volatile emission, a contradiction that challenges basic cometary physics. Statistical analysis reveals the probability of discovering such a large object through random interstellar encounters approaches negligible values, forcing scientists to question either our understanding of object size distributions or the randomness of these visits. Future detection technology. The Vera C. Rubin Observatory in Chile represents the next generation of astronomical detection systems, featuring an unprecedented 8.4-meter primary mirror coupled with the world's largest digital camera. This technological marvel captures images spanning 40 full moons per exposure while maintaining resolution sufficient to detect objects smaller than previous generation surveys. The Legacy Survey of Space and Time will systematically photograph the southern sky every few nights for a decade, creating a comprehensive temporal database of cosmic changes. Advanced machine learning algorithms process this massive data stream in real time, identifying asteroids, transient events, and anomalous objects within hours of observation. The system's enhanced sensitivity will enable detection of interstellar visitors when they're still months or years from closest approach, providing unprecedented preparation time for detailed study campaigns. Rubin's statistical power promises to resolve fundamental questions about interstellar object populations by discovering dozens of new visitors annually rather than the current rate of one every few years. This technology will either confirm that objects like 3I Atlas represent statistical outliers or reveal a previously hidden population. Theoretical implications. The implications of discovering objects like 3I Atlas extend far beyond astronomy into fundamental questions about intelligence in the universe. SETI researchers are developing protocols for analyzing these visitors' behavior patterns for signatures of intentional control or embedded communications. The concept of galactic probe networks gains credibility when considering the efficiency of automated exploration versus biological travel across interstellar distances. Advanced civilizations might deploy self-replicating surveillance systems throughout the galaxy, monitoring emerging technological species while maintaining strategic distance. Theoretical models suggest such networks could map entire galactic regions over millions of years, creating comprehensive databases of planetary development. The timing correlation between humanity's space-age emergence and increased interstellar visitor detection rates raises intriguing questions about causation versus coincidence. Cosmic archaeology theories propose that evidence of ancient civilizations might be found in the form of derelict probes or monitoring stations throughout our galactic neighborhood. These discoveries force reconsideration of humanity's cosmic significance. We may not be isolated observers but subjects of ongoing study by intelligences that achieved technological maturity eons before our species emerged. Future endeavors. The European Space Agency's Comet Interceptor mission represents humanity's first attempt at planned rendezvous with an interstellar visitor, utilizing advanced trajectory prediction and rapid deployment capabilities. International coordination between ground-based observatories and space-based assets is evolving toward real-time global response networks capable of comprehensive data collection from future encounters. NASA's proposed rapid response spacecraft concepts could launch within months of detecting new visitors, using ion propulsion and gravitational assists to achieve intercept trajectories before objects exit our solar system. Project Lyra, designed to pursue Oumuamua, demonstrates the technical feasibility of interstellar chase missions using current technology and careful orbital mechanics. Advanced sample return capabilities would enable direct analysis of interstellar materials, potentially revealing formation conditions in alien star systems or evidence of artificial construction. Future missions will deploy sophisticated spectrometers, mass analyzers, and imaging systems capable of determining composition, structure, and origin with unprecedented precision. These endeavors mark humanity's transition from passive observation to active exploration of interstellar phenomena, potentially yielding definitive answers about the nature of these mysterious visitors. The scientific investigation of interstellar visitors like 3I Atlas continues to challenge our understanding of the cosmos and our place within it. As detection technology advances and analytical methods improve, we stand on the threshold of potentially revolutionary discoveries about our galactic neighborhood. Whether these objects represent exotic natural phenomena or evidence of cosmic intelligence, they've already transformed how we approach the study of our universe. The data keeps coming, and the questions keep getting more profound. Keep exploring with Psi and Y as we decode the mysteries that surround us and push the boundaries of human knowledge into the unknown.